ladies and gentlemen, welcome. This is the video for some additional practice on writing net ionic equations. How do you, first of all, figure out the products of a chemical reaction, and then how do you examine both the reactants and the products to write only those chemical species that are actively participating in the chemical reaction, removing spectator ions, and so on and so forth. So, a reminder. Fundamentally, we've got three different ways of writing chemical reactions. The molecular equation is the way of writing a reaction that you are most used to from reagents chemistry, because it is simply put the equation that shows absolutely everything. It shows the complete chemical formulas of both the reactants and the products. It shows everything. But typically, especially in aqueous chemistry, not absolutely every species is always participating in the chemical reaction. And this is where both the complete ionic and the net ionic equation enters the picture. The complete ionic equation says, let's take strong electrolytes, and if this is an aqueous solution, let's represent them how they actually exist, because strong electrolytes undergo 100% dissociation. So the complete ionic equation identifies those things that are 100% dissociated and splits them up into what they actually will exist as in solution. Net ionic equation takes that one step further, and it will say, well, if strong electrolytes are completely split apart, then that might mean that there are some species that aren't even doing anything in the chemical reaction, and they're just kind of hanging out and watching everything else happen, aka the spectator ions, ions that are unchanged from the reactant to the product side, and let's eliminate them. Let's only show the net reaction. Let's only show those ions, those species, those compounds that are actively participating in the chemical reaction. So, sample problems. I have three examples that we're going to go through. First example, aqueous hydrochloric acid is dropped onto a piece of calcium carbonate. First thing we want to do, figure out the formulas for all the various reactants. Then we're going to think about what the products are going to be. Then we'll identify strong electrolytes, split them up, eliminate spectator ions, and we'll have our net ionic equation. So hydrochloric acid, well, that's easy. We all know what hydrochloric acid is, HCl. And it says calcium carbonate, so we think about what we know. Calcium is +2, carbonate is CO3 -2, so the formula for calcium carbonate is CaCO3. These are our reactants. Looking at this equation, this is an acid and a carbonate. And we did talk specifically about this type of reaction in class. An acid and a carbonate, when they combine, will undergo a double replacement reaction followed by decomposition. And so we're going to get water, carbon dioxide, and a salt. And the salt that we're going to get is going to be the anion from the acid and the metal cation from the metal carbonate. So we're looking at the chloride from the from HCl and the calcium from CaCO3. And you have to think about charge cancellation. Calcium is +2, chloride is -1. So when calcium and chloride combine, we get CaCl2. Before we go on to thinking about strong electrolytes and what we're going to split up, we need to think about phases of matter and, well, balancing, because, yeah, this is not balanced right now. We're going to need two of these so that we can have two chlorides in the calcium chloride, and that takes care of everything else. Two hydrogens, one calcium. The carbon dioxide is coming from the calcium carbonate. So strong electrolytes, phases of matter. Well, it says that the hydrochloric acid is aqueous in the problem. And then it says, and this is kind of key, a piece of calcium carbonate. A piece of calcium carbonate. That is implying that the calcium carbonate is a solid. Water. What phase of matter is water? Water is not aqueous. Water is a liquid. Carbon dioxide, hopefully you feel comfortable saying that carbon dioxide is a gas. And then calcium chloride. Think about solubility. Remember that one of the solubility rules is that halides are generally soluble. Calcium chloride is a soluble compound. Generally speaking, halides are going to be soluble. In this case, we know we've got a reaction We know we have changes of phase of matter from left to right. It's not going to be a precipitate. So we've balanced it, we have identified phases of matter. Now let's identify the strong electrolytes. Remember, strong electrolytes are strong acids, strong bases, and soluble salts. They are not molecular compounds. They are not weak acids, weak bases. They are not solids, liquids, or gases. With that in mind, we have a strong electrolyte here because it's a strong acid. Calcium carbonate is a solid. That means that it is a non-electrolyte. We are not going to touch it. We're not going to split it up. Water is a liquid. That means it's a non-electrolyte. Yes, water itself is a non-electrolyte. If you have pure water, it does not conduct electricity. Carbon dioxide is a gas. That makes it a non-electrolyte. Calcium chloride, on the other hand, this is aqueous. We need soluble salts. This is a soluble salt. This is a strong electrolyte. So the only things that we're going to split up in writing our complete ionic, are the two strong electrolytes, the hydrochloric acid and the calcium chloride. So let's split these up. Now remember, this 2 out in front is going to apply to both the hydrogen and the chloride. So when we split up the acid, we're going to separate the hydrogen from the anion. So I'm going to get H plus and Cl minus, but apply that to, I'm going to have 2 of each of them. And these are both aqueous for keeping the phase of matter from the hydrochloric acid. Do not touch the calcium carbonate. The calcium carbonate is not going to ionize or in any way. It's a solid. Do not touch the water. It's a liquid. Do not touch the carbon dioxide. It's a gas. But now we're going to split up the calcium chloride. Calcium chloride completely ionizes when you put it in water. It's a soluble salt. So it will split into calcium, Ca2+, and chloride, Cl-. But how many chlorides? It will split into 2 because the subscript is 2, so we stick a 2 right out in front there. This is our complete ionic. It's showing how the strong electrolytes actually exist in solution. Now, to write the net ionic, we're going to remove the spectator ions, things that are absolutely identical on both the left and the right. And it's critical. They have to be identical. Even a change in oxidation number means that they are no longer identical and they are involved in the chemical reaction. The only thing that is exactly the same on both sides are the 2 chlorides. So those go away. And we're left with, because nothing else is identical on both sides, 2H plus CaCO3 yields H2O plus CO2 plus Ca2+. And I'm leaving off phases of matter because typically speaking, you do not need to include them. It's seldom required that you include them. I think it's a good idea to include them, but not necessary, because I think including them, especially in the when you're writing out initially, will help you identify your strong electrolytes. Good. Next example. A solution of silver nitrate is combined with a solution of sodium iodide. So we start by writing the reactants, the formulas for the reactants. So we've got silver nitrate. Silver is Ag, charge is +1. Nitrate is NO3, charge is -1. So we've got +1, -1. They're going to combine as AgNO3 in a 1-to-1. And then it's combined with a solution of sodium iodide. Sodium, Na, group 1, that's +1. Iodide, I-. I-1. It's in group 17. It's a halogen, so its charge is going to be -1. So sodium +1, iodide -1. They're going to combine in a 1-to-1. These are the only things that react. Now, when you look at this, I want you to see 2 compounds, silver nitrate and sodium iodide. When you have 2 compounds like this, especially in solution chemistry, this is a double replacement reaction. 2 compounds are going to swap partners. You're going to switch the metals or switch the cations. So we're going to have the silver and the sodium switch places. Keep the nitrate and the iodide where they are. So think about charges. Sodium is +1. Nitrate now, having them swap partners, nitrate is -1. So they're going to combine as NaNO3. Silver is +1. Iodide is -1. Have them combine. It's going to be AgI. So let's fill in phases. Well, first of all, it's balanced already. Everything is one-to-one throughout. So this is a balanced chemical equation. Now let's fill in phases of matter. It says that we have a solution of silver nitrate, so we know that that's soluble, and a solution of sodium iodide, so clearly that is soluble. Now let's think about our products. Sodium nitrate. We want to think, are these things soluble or insoluble? Realistically, that's the thought process for double replacement reactions, soluble or insoluble. Sodium nitrate. There are two reasons why sodium nitrate is soluble. Number one, it's got a group 1 ion, and group 1 ions are always soluble. Number two, it has a nitrate ion, and nitrate ions are always soluble. It's double magic. It's one of our double magic compounds that has got two things in it that are automatically going to make it soluble. Yeah, this thing is definitely aqueous. It's soluble. Which leaves the silver iodide. Halides are generally soluble. However, this would not be a chemical reaction if everything in it was soluble. Because if everything in this was soluble, you wouldn't actually have a reaction. You just have a bunch of spectator ions floating around in solution with nothing to watch, nothing that they can observe, nothing that they can essentially spectate on. Silver iodide has to be insoluble, otherwise we wouldn't have a chemical reaction here. Halides are soluble. Generally, there are some exceptions, and silver iodide is one of them. If silver iodide was soluble, this would not be a chemical reaction. It would just be a whole bunch of spectator ions floating around in solution. So that's how you can know essentially which iodides or which halides tend to be soluble and which don't. Look for things like this, where if that was soluble, it wouldn't work. We wouldn't have anything to write about. So silver iodide is insoluble. That is going to be our precipitate. Now let's identify the strong electrolytes, the things that we're going to separate out. Remember, strong electrolytes are soluble salts, strong acids, and strong bases. There are no acids and bases in this reaction, so we are looking for soluble salts. Hence, we are looking at phases of matter. This is aqueous, therefore it is a strong electrolyte. This is aqueous, strong electrolyte. This is aqueous, this is strong electrolyte, this is a solid, this is a non-electrolyte. We are not going to touch it. It exists in solution as a pair. The silver and the iodide do not separate from one another. We are going to split the strong electrolytes into their component ions. Silver nitrate, what are the two ions? Silver and nitrate. So split it as such, Ag plus NO3 minus, and there's simply one of each one, so that's all we need to do for the split. Sodium iodide, the two ions are sodium and iodide. Again, just one of each, so we're good. Sodium nitrate, what are the two ions? Sodium and nitrate. And we've got the silver iodide. We identified that as a solid, so we do not touch it. We're going to keep that one together. As I was saying in AP Chemistry, keep it together, people. Keep it together. And now we're going to eliminate things that are exactly the same on both sides of the arrow. The spectator ions, the things that don't actually change. We've got a nitrate on both sides that isn't actually doing anything. And we have a sodium on both sides that isn't actually doing anything. These are our spectator ions. The silver and the iodide, on the other hand, exist as individual ions on the left, but exist as a compound bonded together on the right. They're insoluble, so they're not being separated. So that means when we write our net ionic, it's going to be Ag plus I minus goes to Agi. And again, the benefit of writing the net ionic is essentially knowing that if this is the reaction that you want, what you're really getting is the silver iodide product. It means that with this reaction right here, I don't need it to be silver nitrate. It could be silver something else that's soluble. It could be silver acetate. And I would still have the same net ionic. it means that I don't need it to be sodium iodide, I just need an iodide. It could be potassium iodide, it could be lithium iodide, because the sodium actually canceled out. The nitrate and the sodium canceled out. So their identities ultimately didn't matter, which is useful information because it means that if I want to do this chemical reaction right here, and I go to the stock room and I realize we don't have any sodium iodide, I'm not going to panic because I know that the sodium itself is not important and I can replace it with potassium iodide, which we do have, and I'm still going to get the same net ionic. That's the benefit of understanding net ionics and understanding that what's really going on here, it's just based on the silver ion, the iodide ion, making silver iodide, and that's it. So I hope this helps as you're practicing writing net ionics. It's definitely a skill, and it's a very important skill. So make sure you feel comfortable with that. We'll be testing you on that later this year.